back in section 1 of chapter 11. We're going to do our best to finish up this section in this video, and we're going to start off with a little summation notation, which I mentioned just briefly at the end of the last video. Sigma notation, and they use the term sigma because they're using the Greek letter, the capital Greek letter sigma, for the symbol that represents a sum or a series. So it's given a sequence, a sub 1, a sub 2, a sub 3, and so on. The nth partial sum, which means the sum of the first n terms of the sequence, which they label S sub n, is a finite series and is represented by, notice here, S sub n is equal to, this is the sigma notation. Underneath it says I equals 1 to n of a sub I, and that's equal to a sub 1. So you start with the number here and substitute it in for this variable I, which we call the index. A sub 1 plus, the sigma represents a sum of terms, plus then you go to the next number, a sub 2, then you go to the next number, a sub 3, and you go to the next number to top out here at this number that's at the top of the sigma, a sub n. This expression right here we refer to as the summand, and that's what tells us, that's the expression that we plug in these values, starting with the lower limit of summation, which most of the time is either a 0 or 1, but it doesn't have to be, it can be any number. And the I, and we sometimes use the lowercase letter I, lowercase letter n, lowercase letter j, lowercase letter k, which we refer to as the index. And then the number at the top is what we refer to as the upper limit of summation, 1 being the lower limit of summation. So this is where we start and this is where we finish. Alright, now what I'm going to do is I'm going to take this expression here and I'm going to write the terms, and then I'm going to go ahead and evaluate the sum, and I have 3 of them here that we'll look at here quickly. This first one is the sum as I goes from 1 to 5 of the expression 3i plus 1. So I start with 1 and I substitute it in. So I have 3 times 1 plus 1. And then I add to that, when I plug 2 in, I have 3 times 2 plus 1. And then I have 3 times 3 plus 1. And then I have 3 times 4 plus 1. And then I have, and I'm running out of space here, so I'll bring it down here, the last one where I substitute in the upper limit of summation, and that would be 3 times 5 plus 1. So that's going to be equal to 4 plus 7 plus 10 plus 13 plus 16, which is 11, 21, 34, 44, 50. It adds up to 50. And that would be my sum. So I write out the terms, here they are, and then I actually find the sum here. Here it is. Now this next one, you can see it has, as part of the summand, it has the negative 1 raised to a power, which indicates to me that these are going to be an alternating terms in sign, positive, negative, and so on. And since we are starting not with 1 but with 2, it looks like if I put a 2 there, I have negative 1 to the 3rd power. I start off with a negative. So this is going to be equal to, starting with a 2, this will be negative 1, and then if I put a 2 there, I get 1/4, so this is negative 1/4. Make sure you can see that. And then if I plug 3 in, now notice my upper limit is 5, so I don't have very many terms, which is good because of the fractions. But if my upper limit is 5, I'm only going to have 4 terms. I go to 3 next. That would be 3 plus 1, 4, negative 1 to the 4th, that's positive 1, so it's going to be positive, so it's going to be plus. And then if I put a 3 in here, I'm going to get 1/8. And then it's going to be minus, and it looks like 1/16, and then it's going to be plus. The last one is going to be 1/32. Looks like my pen is starting to fail here. Oh, there we go. So my common denominator is 32. There are my terms here, but my common denominator is 32. So I'm going to have negative 8 plus 4 minus 2 plus 1. So what does that give me up top? Negative 4, negative 6, negative 5. So I end up with negative 5/32 for my sum. And then again, here are I write out the terms, and here's the sum. Here are the terms, and here's the sum. Be sure to show your work. The next one up is kind of a weird looking expression in that the index, which is k here, is not found in the summand. The summand is just 4. So if I was to plug 1 in, well, there's really no place to plug in, and I just get 4. And then I plug 2 in, and again, there's no place to put it, so I just get 4. And 3, I put 4, and 5, my last one. So I end up with 20. Kind of a strange one here, but as it turns out, we have some properties of summation, and you will see here that this particular one pairs up with this property that I'm going to talk about here right at the end. Now, I have two problems in which I am giving you a series. Remember, a series is where you add up the terms of the sequence, and I'm adding up these terms, and I want to use sigma notation to represent this. So I kind of notice I got some consecutive factorials on top, and on the bottom it looks like I've got multiples of 7. So I'm going to put this sigma here, and I'll use I. I like to use I myself. And I need to get multiples of 7, starting with 7. So I'm thinking in the bottom 7i. Because that way when I is 1, and I want to start with 1 here. When I is 1, I'm going to get 7. When I is 2, I'm going to get 14. When I is 3, I'm going to get 21. But in my numerator, I don't have 1 factorial, I have 2 factorial. Then it starts to increase. So I'm thinking on top here, I'm going to have I plus 1 factorial. Because that way when I plug 1 in, I'm going to get the 2 factorial. When I plug 2 in, I'm going to get the 3 factorial. And I continue this until it looks like I plug in n right there. Now you kind of look at this general term here in terms of n, and you look at my summand, and you can see the similarity. They don't normally make it that easy for us. You might get something more like this problem, where there are no, it's finite, and there are no variables somehow in like a general term. But I do see some patterns. I see an alternating series here, starting with a negative, and I notice that my denominators are powers of 5. 5 to the first, 5 to the second, 5 to the third, 5 to the fourth. And my numerators look like they're perfect cubes. 1 cubed, 2 cubed, 3 cubed, 4 cubed. Now you got to look for the patterns here. So I'm going to go from I equals 1. It looks like I only have 4 terms. I have to get the negative to work right. So I want to start out with a negative. So I need this to start out with an odd power of -1. So I'm just going to put the I there. That way when I plug 1 in, it comes out to be negative. Now the denominator are powers of 5. So this looks like this is going to be 5 to the I. Because that way when I plug 1 in, I get the 5. If I plug 2 in, I get the 25, and so on. And then I need perfect cubes up top. So this looks like this is going to be I to the third power in the numerator. Because that way when I plug 1 in, I'm going to get the 1. If I plug 2 in, I'm going to get the 8, and so on. And there's my expression. Now, they can get really complicated. So you got to look for the patterns and think about it for a while. They're not always just going to be so obvious. These two weren't too bad though. And that leads us to the properties. The properties of summation. So if a sub n and b sub n are sequences and c is a real number, then the sum, notice I'm doing series here, then the sum as I goes from 1 to n of a constant c is c times n. That's what happened here. I had a constant. And it turned out to be this constant times 5 times n. So 4 times 5 gave me 20. That's this property right here being demonstrated. And then the next one says that if you have a sum and you have a constant times the term here, a sub I, you would get the same thing as if you brought the constant out as a factor of this entire expression. Because every one of the terms is going to have a factor of c, so it's like you're factoring out the c, just putting it out in front, ready to distribute later on. And then this one here, it's actually 2 in 1, because you can think of this with a plus or a minus, and that is if you take in the sum as I goes from 1 to n of a sub I plus or minus b sub I, it's the sum of from I going from 1 to n of a sub I plus or minus the sum as I goes from 1 to n of b sub I. These two guys here, when you have these two properties, these are called the linearity properties. And what I like to think of here, especially for the top one, when you're adding, is that you have the sum of a sum, and it equals the sum of the sums. That's bad. All right, so that finishes up this section. We're gonna give you a chance to try some problems here before you get to your assignment. So do the practice problems on this assignment, I think, to make sure that you get familiar with this as we're finishing up this this last bit here in the course. Make sure that you feel comfortable with this, and that's why you got to practice practice, practice.